Thank you for your kind introduction, Mr. Chairman. I'm Kota Sugisaka, a master student of Kyoto University in Japan. My presentation title is Dislocation, Multiplication, and Structures in Micro-sized nickel single crystal under low amplitude cyclic loading. Let me begin with the introduction of this study. Critical resolved shear stress is the yield stress resolved into the primary slip system of a single crystal. And shear SS is constant at the bulk scale. However, it is widely known that as the diameter of single crystal decreases to less than tens of micrometers, it becomes larger. As for copper single crystal, shear SS of the bulk is less than 1 megapascal. However, as the diameter decreases to 2 micrometers, it becomes 40 megapascal, and it ultimately becomes the 500 megapascal as the diameter of it decreases to 100 nanometers. The underlying mechanism of the phenomenon smaller is stronger in monatomic loading is considered to be the inhibition of dislocation activities in nano to micro-sized single crystals. In such smaller single crystals, there are less numbers of initial dislocation sources, and dislocations can be easily emitted from the surface. And the activation of single dislocation sources are also considered to be contribute to such high CRSS. By the way, it is also interesting that how the material strength depends on size and the cyclic loading. In other words, is the phenomenon smaller is stronger also too under cyclic loading. Our research team has been working on fatigue of micro-sized metals. And this is a movie of in-situ tension compression cyclic loading test. We conducted such tension compression cyclic test on micro-sized specimen by developed loading apparatus suitable for conducting such a test. We revealed that copper single crystal with a square cross-section plus size of 2 micrometers fatigue at resolved shear stress amplitude of 10 megapascal. And that was about 1/3 of fatigue crack initiation limit of the bug. So the smaller is not stronger under cyclic loading. And moreover, micro-sized copper single crystal fatigue the stress amplitude lower than CRSS of such size. Because fatigue metals appeared as a result of accumulation of finite plastic deformation, it is questionable why micro-sized single crystal metals fatigue the stress amplitude clearly lower than CRSS in monatomic loading. The purpose of this study is to explore the mechanism of that micro-sized single crystal metals fatigue at the stress amplitude lower than CRSS obtained in monatomic loading test. First, we conducted tensile tests and compare the result with previous research to confirm the reliability of our own experimental system, and then conducted cyclic loading tests of different numbers of cycles to multiple specimens and observed dislocating structures using TEM. We use pure nickel single crystal as a material, and the plate was annealed at 1173 Kelvin for 30 hours. The specimens were fabricated by focused ion beam FIB processing system. The damage layers induced by FIB processing was removed using argon ion milling. The gauge part of specimen has a square cross-section plus size of 2 micrometers and the height of 6 micrometers. Specimens were fabricated for a single slip system, the only slip system before we reactivate. 8 specimens with the same dimension and crystallographic organization were prepared. The experimental system was composed of our developed loading apparatus, field emissions SEM, and the controller. The developed loading apparatus was composed of a load cell, a piezoelectric actuator, a displacement sensor, microgripper, and staff. Tension and compression loading was subjected to specimen by gripping the head of specimen using micro gripper. To eliminate equipment dependence, we conducted tensile and cyclic loading tests using both the same experimental system. First, we conducted 3 tensile tests, and then conducted cyclic loading tests under constant displacement amplitude to satisfy the resolved shear stress amplitude lower than shear SS from tensile test. 5 specimens were subjected to cyclic loading test, but each specimen was subjected to different numbers of cyclic loading. After cyclic loading test, these specimens were seen, and we observed the dislocation structures using ultra high voltage transmission electron microscope. So now let me talk about the result and discussion of this research. First, we conducted 3 tensile tests, and obvious elastic plastic transition was observed. CRSS was evaluated be in the range between about 70 to 100 of megapascal. And the result was in very good agreement with the previous research from the stress versus diameter plot. We can state that we can confirm the reliability of our one experimental system. And we determined the displacement amplitude in cyclic loading test to satisfy resolved shear stress amplitude of about 40 megapascal. That was about half of CRSS in monatomic loading. And then we conducted 30,000 of cyclic loading tests. That was the maximum cyclic number in this study. The resolved shear stress amplitude was about 36 megapascal, clearly lower than CRSS. However, as we expected, inclusions and exclusions with a depth and height of 300 nanometers were formed. Similar with copper single crystal, micro-sized nickel single crystal also fatigue at stress amplitude lower than CRSS. To reveal the underlying mechanism, we conducted another 4 cyclic loading tests with less cyclic numbers and observed the interior. After the first cycle, several dislocations were observed in the specimen. However, the dislocation density was not apart from that of annealed metals. But after 10 cycles, the number of dislocations increased in the wall region of the specimen. Some dislocations tangled or intersected each other. After hundreds of cycles, the number of dislocations still increased, and self-organization of dislocation began. Self-organization of dislocation produced this black high dislocation density region in some parts. Based on this result, dislocations were in motion and multiplicated at a stress amplitude lower than CRSS in monatomic loading. Repeats of microscopic movement of dislocation would increase the opportunities for cross slips or dislocation interactions, which are considered to contribute to dislocation multiplication. At following cycles, the high dislocation density region localized in the central part of the specimen, and finally, a dislocation wall parallel to the longitudinal direction of the specimen was formed in the central part of the specimen. And fatigue damage like intrusion extrusion was formed. As the dislocation structure finally formed in micro-sized nickel single crystal was composed of a dislocation wall made of edge dislocation and screw dislocations in the low dislocation density region near the surface. And this structure is similar with ladder-like structure in the bulk. Because screw dislocation in low dislocation density region can easily move back and forth and produce larger plastic deformation, The formation of ladder structures causes fatigue crack initiation in the bark. In micro-sized Nikkei single crystal, the peculiar dislocation structure similar with ladder-like structures were formed under low stress amplitude due to the influence of the size and surface. And the plastic properties of such peculiar dislocation structure causes the formation of fatigue damage under low stress amplitude. In this study, to explore the mechanism of that micro-sized single crystal fatigue at the stress amplitude lower than shear SS, we conducted tensile and cyclic loading tests on micro-sized Nikkei single crystal. The shear SS in tensile test was in the range between 17 to 100 megapascal and in good agreement with the previous research. And on the cyclic loading test, dislocations were in motion and multiplied by a cyclic loading. Even the stress amplitude was lower than shear SS. And as the number of cycles increased, peculiar dislocation structures were formed, and it caused appearance of fatigue damage. That's all of my presentation. Thank you for your kind attention.